Tema candente. Okay, so let's start. Welcome everyone. Also all those who are following the seminar online. Thank you for coming. Well, today Pera is gonna tell us a little bit about power grid dynamics related to the blackout in relation with what we do here at the FIS. Okay, so yeah, without further ado, let's go ahead.
Thank you, Damian. So the title of the talk it reflects what I expect to achieve at the end, is that to give you some background to be critical when you hear news about the events that happened on the blackout of the April 28th. Okay, so what happens? Okay, this is official data from the webpage of Red Eléctrica Española, which I'm going to describe later. This is the official institution that controls the power grid in Spain. Okay, everything was fine on the sunny day of April 28th, or apparently fine, until 10:30. That's the demand. All the demand was met here. So, by the way, here there are three lines. One is the demand, the real demand. Okay. The green one is the expected demand, that is expected, is forecasted before. And then this is the red one is the program demand. There is a dispatch every 15 minutes, and they program the plants to satisfy this demand. Okay, so far so good. And the official data reports that 5 minutes later, the data is only every 5 minutes. Okay, I'm not saying that the Red Eléctrica does not have more data. It is the data that is publicly available at the web page of Red Eléctrica. Okay, so 5 minutes later, the power, the demand which was satisfied, fell by 11 gigawatts. Okay, so just to make it clear, 1 gigawatt is a typical size of a nuclear power plant. 1 gigawatt is the typical consumption, peak consumption on summer in the Balearic Islands. Okay, that's the size of 11 gigawatts, is 11 times that. And that's a lot. That's a blackout. Okay. Now, of course, from here we can only say that this happens in 5 minutes, but most probably, of what's been reported after, for some in other places, the event was much faster. This is not a single event. There is no 11 gigawatts power plant in Spain or in the world. Okay, so this has to be a cascading of events that led to the loss of that much power. Okay, cannot be a single event. So, what the newspapers report? This is I took the 7th most read newspapers in Spain according to Wikipedia. Okay, I don't want to be accused of using newspapers according to a political or whatever. They took according to Wikipedia, okay, the ones that are most read are the 7 that I'm going to show, in the order that I'm going to show. Okay, so this is a place, it says that there is a massive massive blackout on the Iberian Peninsula. Now this is 20 minutes, the big blackout. And here you cannot see it, I'm sorry, because it's disproportionate. It says an entire country in the darkness. So in the Balearic Islands that the blackout was not affected, we are not in the country, or we are, I don't know, we are not there, okay? Canarian Islands either, Ceuta and Melilla neither, okay? So we are not, we are zero. We are not in the country where, so, I mean, I will go. What I'm showing here, sorry for that, this is mainland Spain generation. Sorry, demand. I will show this generation later. Balearic Islands demand is not shown here. Canarian Islands is not shown here. It's not included in this. I'm going to go that. I'm going to go to that point, okay? Okay. This is what is the data. This is what it has been said. I'm going to go point by point. This is a window to choose the metro station that has the name of the house of the prime minister can be considered a little bit, say, tendentious, okay? Of course, again, España, o España, La Vanguardia, España Apagada, okay? So, now, the fifth most read paper is El Periódico, España Paralizada, Spain Paralyzed, Chaos through Spain, ABC, o ABC. La Voz de Galicia, Spain and Portugal suffer the multiple consequences of the collapse due to the lack of energy. Energy, I mean, the electrical energy, but the cars were still running, that's also energy, okay? Okay. So this is what is said, okay? This is what is said, and this is what, so each of these newspapers, each of these 7 newspapers has a daily readers according to EGM, okay, which is one of the official statistics, over 600,000 readers every day. The El País has over 1 million, okay, but the last ones, all of them are over 600,000, and I stop here. Okay, so we had a blackout, okay, and it was reported. Now the first thing, oh, this can happen, this never happens, this has never happened before, this, yeah, okay. This only happens in, I don't know what kind of sort of country, so let's take US, okay, which is not a country that is in the third world, or it should not be. That's another question, I don't know. Anyway, so in November 1965, there was a blackout which affected the northeast US and the Ontario region in Canada. Okay, this is the report of the New York Times, and this is the report of this. If you remember when the newspaper was titled Chaos in Spain, I don't think this sort of images were seen, has been reported in the blackout in Spain. Okay? Okay. Anyway, okay. Sorry? There is people in the running, there is people that on the floor that cannot, that not moving, they're just lying there, who just completely lost. I mean, it could be that in Spain there was some people in the trains, there was a big mess in the people in the trains or whatever. Okay, that's true. Oops. Okay, that I don't know what happens here. Okay, so I best restart. If this happens, I best restart the escape in the LibreOffice because I no tinc en cloud. No, bueno, tinc aquí en cloud. I have everywhere. Okay, got it. So in August 23, 2003, there was another blackout affecting Northeast US, Ontario. And in this case, it affected 55 million people. The New York Times reported again that, and New York Times, sorry, the Times, the Newsweek Time, entitled Blackout, you cannot see what it says below, but it says, can it happen again? I don't know. Did it happen again? Okay, not in this particular region, but about 1 year later in Italy, okay, there was one that was bigger. And the problem was originated in Switzerland. There was a tree falling over the line in Switzerland. Italy was running with less generation than demand, importing electricity from Switzerland, and that triggered a cascading of effects that all the power grid. See?
Say something there. Say overloaded.
Yes.
They give a why.
I'm not saying that there is no reason. There is always a reason. Yeah. There is a different reason here. There is a different. I'm not going to explain all the reasons because we don't finish. Okay. There is always a trigger. There is always a trigger, and there is a situation in which the system is close to be critical. Okay. Because if not, you don't get a cascading of effects. Okay. That's the common things. Okay. So in this case, in Italy was generating less than the demand, was importing electricity from the north part of Europe through Switzerland, or importing from Switzerland may be importing from somewhere else. Okay, and well, there was 57 million people affected by this blackout, and this one maybe you know a little bit more, or you are more familiar because it is studied in this famous paper in Nature, in the Nature journal, okay, by the group of Eugene Stanley, okay, and basically they were part of the problem, and part of the problem that triggered the massive failure, and then it happened, it was a handicap for the recovery, is that when the electrical grid stopped working, the communications grid stopped working, and some of the electrical nodes were remotely controlled by. So you need the communication network to operate those nodes, but you cannot operate because you don't have a communication network. Okay, so it's a sort of, and it was modeled as a multi-layer network. Okay, one network for the power grid, one network for the communications. Okay, with some nodes that have communications and grid and so. Okay, so that was so again. So here we start to see that this is a complex problem, might involve more than one kind of things, more than one kind of networks, and that the system is operating in a regime in which, for instance, Italy was lacking generation, and something happens. Now, can it happen again in US? Well, why not? I mean, in Texas, 2021, the Italian one lasted a few hours, 1 day or two, but this one lasted 17 days, okay? So it was a little bit more problematic, okay? Was it not a blackout that blacked everything? It just happened that for 17 days, okay, there were parts of the cities in Texas that were without electricity, okay? In particular, there were about 4.5 million homes. So that will give you an idea of how many people were affected, okay? Without power for several days, okay? That's the image before and after. This is Houston, okay? And that's Houston, we have a problem, okay? Officials, including the governor, blame immediately the wind turbines because there was a severe weather situation, and they blamed the wind turbines that were frozen and the solar panels that were frozen as the responsibles of that the grid was not operating properly. Guess what? That was not correct. Okay? This is taken from Wikipedia, which is a place where people edit everything and there is many back and forth. Okay? So the data, the official data, show that the failures were not because of that. The main failures were because the traditional power sources, mainly the ones on natural gas, were frozen. And of course, also affected to the wind turbines later. Okay? So that's the fact. And this also, I mean, has been studied. It was studied in this paper, Cascading Risk, Understanding the 2021 Winter Blackout in Texas. Cascading Risks. Okay? So it's something that triggers the failure of a cascading failure until something gets very big. Okay? Okay, so let's go for the largest blackouts, okay? Well, the largest blackout was in India in July 30, 2012, okay? It affected 400 million people. And there was not enough with that on the next day, India broke the record and set a new record on 620 million people affected. Okay? The service was restored in 1 day or two, depending on the areas. Anyway, this is the part of the country that was affected. It was not the whole India because that's much more people. This is the list of the blackouts. This is taken from Wikipedia. It's not just the number of people, it's also the number of people and the duration of the blackout. Okay, it takes a little bit of sort of everything. Okay, so okay, here we have Pakistan. Of course, you know that India and Pakistan are always confronting. So if they have one, why do not we cannot have another one? So let's get it there. Okay, and then India and whatever. Okay, so Bangladesh, which also there, Pakistan, Bangladesh, Pakistan, Hawaii. Okay, Brazil. In 1992, there was one in northern Brazil that affected 97 million people. In 2015, in Turkey, that's the power grid of Turkey, okay? It was a blackout that affected 70 million people. There was another one in Brazil and Paraguay in 2009, 60 million. September 28, 2003, Italy is the one that I have just commented. The one of the Northwest US and Ontario is that I have commented. And number 16 is us. Okay, we finally got close to the podium. No, it's very difficult. We don't have, we don't have that, no, we can't. So this is the number 16 with the same numbers affecting the same number of people approximately than the one in Northwest US and Ontario. Okay, and you might ask, who was previously the 16? Okay, then now is the 17. is one that took place in 2019 in Argentina and Uruguay and Paraguay that affected 48 million people. Okay, this is an image of that. Okay, and of course there are many others. Okay, and these are only the big ones. Okay, there are many blackouts of many sizes. So this happens. It happens in many places. It might happen more frequently in infrastructures that are not taken care as it should be, in places where they operate close to the limit of the capacity. Okay, but it can happen anywhere. It can happen. There has been also blackouts in Germany, the one triggered by cutting a cable on a channel which is not that big. Okay, but some point happened. Also, if you look at the dates, you see that most of these big blackouts are in the 21st century. Okay, so it's not something of the past, something of the present. So, okay, this is the blackouts. So let's go back to the Spanish blackout. Okay, now we have the context, we know all that. Let's go back to the events on April 28th. So what's the system that we have to study? Okay, what is the system we want to understand? Okay, what is the system? Okay, so let's see. So the system should be, so what is the system? The system should be something like this. Okay? The system should be something like this. This is the Iberian Peninsula high voltage grid. This connection here is a DC cable, direct current. So it's connected, is not part of this. This is an independent electrical system. This is a big system. Now, as you know, the electricity that we use is an alternating current, okay, AC, which means that electrons, because after all, electricity is electrons moving, okay, we are physicists, so electrons move back and forth 50 times per second, okay, 50 times per second, they move back and forth. So they oscillate, the displacement oscillates at a frequency of 50 hertz. And this thing, which has a size of 1,200 kilometers, okay, can be seen as a large set of couple oscillators. Synchronizer, all of them at the same frequency, all of them with a phase difference that is fixed. Okay, phase lock. If you want a large model of couple oscillators, here you have one of them. Okay? Here you have a large system of couple oscillators. Nobody wants to experiment that synchronization transition in this system. Okay? They will not let you do that experiment. Okay? What we want is that they operate in synchrony all the time. Okay? Now, so is this the real system that we have to study? Not quite. No, this is just a part of it. Okay, because in fact, this is part of the continental Europe synchronous area, which is the thing that is shown in green. Okay, the name is a little misleading. Okay, but all the countries there shown in green, look that the Balearic Islands is not there. Okay, yeah, it's here, but it's not green. Okay, because it's not in synchrony. All that area, all the green area, from Casablanca to Lithuania or whatever over there, is operating in a synchronous mode. You have oscillators across all these countries, all of them synchronized. Okay? That's the system. There are other big or large grids. For instance, the one in orange is another grid that comprises several countries. This is another one that comprises several countries, which are interconnected. And Okay, this is one of the biggest, but not the biggest, the largest one, because the largest one is in China and in Asia. Okay, UK is not synchronized with the European Union and the rest of the countries here, and neither, and the Baltic countries has another grid which is synchronized. Despite that, there is DC cables, okay, direct current, that can translate power from one grid to the other without translating synchrony. So this is the system plus the external influence of the energy that is transferred by the DC cables. Okay, one either to the continental synchronous area or out of that. For instance, there is a cable that connects to Mallorca, and this transfer energy, not synchrony, but the energy is transferred as a direct current by the cable to Mallorca, and we get the energy here, for instance. Okay, so that is something like a loss for this system. Okay, extra load. Okay, so it's quite a big system. Okay, it's quite a big system, and if you want to analyze all the data for all the substation in this system, you need quite a while. And that's the real system, because that is what is interconnected. Now, who manages this system? Well, this system is managed not as a single thing by one organization, rather something like air traffic control. There are zones, and there is somebody who manages each zone. Okay? So what happens is most countries have what is called a single transport system operator. Okay, TSO. The TSO is the responsible for the grid stability and synchrony in his territory. For Spain, that's Red Eléctrica. Okay, so Red Eléctrica is the responsible that the grid in Spain is synchronized and operates at 50 Hertz. There are TSOs in all the countries. Some countries, for instance, in Germany, have 4 TSOs. They have divided the country in 4 zones, and in each zone there is a different TSO that takes care of that. Okay, this is structure of having somebody that takes care of all the transmission grid, the large voltage transmission lines for each part is adopted across all this synchronous area. Okay. Now, there is also something else. There is ENSOI. ENSOI is the European network of transmission system operators for electricity. Okay, so there is an association of TSOs. So Red Eléctrica is member of ENSOI, and the German operator for the TSOs, and the Portugal TSO, and all that. Okay, and ENSOI, the members of there, not only operate this grid, they also operate the Baltic grid, the UK grid, the Iron grid, and the Iceland grid. It's not here, but it's also operated. The operator of Iceland is also member of ENSOI. Okay, so ENSOI is a forum of TSOs. Okay, and all or most of the operators in here belong to ENSOI. Okay. So this is when you hear, if you hear somebody has asked for a report from ENSOI, this is, for instance, there was some proposals by some political parties to ask for a report from ENSOI. This is the institution. Okay. It's a European level scale system. Now, so that's the context. Now let's talk a little bit about power grids, okay? And let's start doing some modeling and other things. So what power grids, I mean, we have described that, but now let's see what is the ingredients of the power grids, okay? So power grids are composed of many things. Okay, many things. To begin with, there is some plants that generate the energy. Okay, this is generation. Then this is owned by some companies. Okay, these plants. They bring the energy to the transmission system, the high voltage power lines. Okay, which is managed by Red Eléctrica Española. In Spain, is managed by the TSO in the respective area. Okay, so this is where the TSO. Now, then of course, we don't consume electricity at 400,000 volts, okay, or 200,000 volts, okay. That would be a little bit dangerous, okay. So we have to take this voltage down, okay. And then we have some substations and and conversion to lower voltage, mid voltage, low voltage, whatever. Up to is the distribution. The distribution is the power grid that arrives to IFISC, the power grid or to the university, the one that arrives to your home. Okay, this is done by another company that also has an area. Okay, so for instance, here it is Endesa. Okay, in solar it is Gas de Solar. Okay, and in different parts of Spain could be, or the other could be anyone. Okay, this is not Red Eléctrica, and even that distribution is done by Endesa. It's not the same Endesa. Officially, it's the same, but I mean, officially, it's a different company from Endesa generation. Okay, this distribution is part of the same business association, but it's not the same company. This one only takes care of the grid to your home, but it does not bring you the electricity. You don't pay to them. You pay to the electricity provider, which is another company. Okay, that you contract the electricity with them in the same way that the telephone. You can contract your telephone or your optical fiber in your home to whatever, and there is only one company that takes care of the maintenance of the optical fibers in the zone where you live. So this is the compañía comercializadora in Spain. Okay, so the ones that sell you the electricity. Okay, again, this is Iberdrola, Endesa, whatever, but this is different in principle to the generation and the distribution. So, for instance, you can contract the energy with Naturgy, for instance, here, having the distribution in Mallorca by Endesa, and in this case, the generation is also Endesa. Okay, but in other parts of Spain, this could be completely different. So, when the commercializer charges you for the electricity, it pays to the distribution, pays to Red Eléctrica, and pays to the generation. Okay? When somebody says peajes, the electrical peajes, or the electrical tolls, is the payment for the distribution and for the transmission. Those are the toll, the peajes. Anyway, so you see that there is many things, okay? And we have lines of many kinds, and we have many devices consuming, and we have many ways of generation. But there is one thing that is not there. I mean, there is a little bit, but it's not that much. It's storage. Storage. We don't have a storage at large scale. So what this means? That at every point, at every time, we have to generate whatever we consume. Exactly what we consume. If we don't do that, and I'm going to explain why in a moment, okay, you know what? If we don't do that, the frequency increases or decreases. If generation is larger than consumption, the frequency increases. If generation is more than consumption, the frequency decreases. Changing the frequencies is something which is not something which should not be taken as a minor consequence on the grid, because remember, we have this whole grid completely synchronized, okay? So we cannot start changing the frequency on a node, okay? Because we have a problem. So that's why the frequency of the grid is monitored at all time. And For Europe, or for the European synchronous area, there is a statutory limit that the frequency cannot deviate from 50 Hz more than 0.15 Hz. Okay? UK, for instance, has a larger margin of maneuver. Okay? In Mallorca or in the Canarian Islands, this is just a recommendation. Okay? According to the Spanish official rules, for Mallorca and for the Canarian Islands, it is advised not to go beyond this limit, but if you go beyond that limit, it's not that bad. For the Europe power grid, if a TSO goes beyond that limit, then NSOE might require, what have you done, okay?
And what happens to the frequency goes to 52 Hz?
April 28. Eh? Let me show, okay? Because it's, let me show, okay? I will go to that, okay? So, okay, so that's the situation, okay? This is the thing. See, we have a big system that has to be operating in synchrony with time margins. And we know that the energy that we are demanding to the system might change because I might go there and switch on a light. And somewhere there can be a power plant that increase the generation to cope with that. Okay? And I'm not going to call Red Electrica, look, I'm going to switch on a light in a few minutes, okay? Please be ready. I'm not going to do that. So, you know, I mean, you seem not convinced, but that's how it is, okay? But that's okay. This is a balance. So we have a load which is variable that might change, and we are adding to the grid renewable generation, which some of them, for instance, the wind generation and the photovoltaic generation cannot be fully regulated. Okay, you don't have a knob to tell the wind to blow more or less at a given time. Okay, you have relative margins of corrections or whatever with electronics and that, but it's not the same that having a control of a power plant which is fed with gas, for instance. Okay. So the mechanism that has been traditionally used and is still used most of the time is that generation adapts to consumption. Whatever you demand, the generation, the companies that generate energy give it to you. Okay? So this requires to have extra generation, extra capacity ready. So you have a power plant of 100 megawatts, you might be operating at 80 megawatts so that you are ready to increase the power to 100 megawatts whenever needed. Okay? You don't operate at the maximum, or we told you before, because you have to have a margin to maneuver. And you have fast units that can start from cold very fast when needed, okay, which is what is called the non-spinning reserve. So it's a reserve which is not spinning at that time, it can be switched on whenever needed. Like for instance, when there is a shortage at the university, okay, the generator, the diesel generator that the university starts, that takes a couple of minutes, okay, and then you have main power there. In the meantime, if you want no interruption, this has to be maintained by a battery or a system of storage, okay, that covers that time that the generator needs to start, okay? So if you have conventional power plants, you might increase the power of the power plant a little bit above, and then meanwhile you start another power plant, okay, which is fast to start, okay, and then you recover this extra power, okay? That's the non-spinning reserve. Yes? Spinning. Yeah, fully. I'm going to go to the questions in a moment. The spinning is that rotating at 50 Hz. Ready for whatever is taken. That's the spinning reserve. So it's rotating mass that is not operating at full capacity, okay? So you have at 80% of the capacity or whatever, and you can put more fuel there whenever you want, and it starts rotating with providing more power, okay, for the consumption. Okay, so this is very nice. This is and we are in a framework, okay, because the power grid is a technical system, but it's a technical system that is entangled with the society, and this is why blackouts are so relevant, okay, because basically most of the things cannot work without electricity, and people without electricity at these days does not know what to do. Okay, so there is already a link between this technical and society, and I'm going to provide another one because we have a pressure. Sorry, before going to that, what I just want to say another idea that I think is important is that the frequency stability is an indicator of the quality of the service because it's an indicator of how much disbalance there is power and consumption. But I'm going to go that. Now, I'm going to say about this society interaction with the technologies. Now, we need to reduce CO2 emissions because basically we are increasing the temperature of the planet, and it is recommended to reduce CO2 emissions, okay? So what we have to do is stop consuming so much conventional fuels, okay? So we have to stop or reduce the amount of power plants that consume fossil fuels, but that's not enough because there is a lot of consumption of fossil fuels in transportation. So we have to electrify transportation. So we have to increase the production of electricity. Okay? That's what society demands. Not, I mean, in general. There might be some people that they don't agree. There is, I mean, people that decide that drill, baby, drill, but okay. But most of the people will understand that we want to go to a decarbonized society. Anyway, the International Energy Agency predicted a 45% electricity demand increase in demand of electricity between 2015 and 2040. Okay, and because of the things that get progressively electrified. Okay, so we want to increase the penetration of renewable energies. We want to produce, we want to produce more electricity from renewable energy sources. We want to increase the amount of energy that we produce. And most of these renewable energy sources that we have available, I mean, hydroelectric is a renewable energy source that is well known and is not variable, is very stable, and it can be very controlled very well. In fact, the first power plant in Mallorca was a hydroelectric power plant. Okay, Sa Costera. Okay, so, however, all the hydroelectric resources in most of the countries have been already exhausted. Okay, so we need something else. So we reduce. So we have to go to resource to renewable energies such as wind and sun. Yeah, see, which are not which are variable. This introduces fluctuations. If we reduce power plants, we reduce the control capabilities, and the inertia, which I'm going to call in a moment, is also reduced and makes the system more vulnerable. So, let me put some questions here. I think that I'm not going to cover all what I wanted, but that's okay. Let's consider the power plant, okay? Say an oil or gas burning power plant, conventional power plant. You burn the gas, okay? And then you burn the gas, you have you put the vapor on a turbine. The turbine has is doing to a generator, okay, and then you generate the electricity. This is the rotator of the generator, okay, the axis from the turbine goes in this way. There is here a magnet, okay, in this case it has 2 poles. Here we have three windings, which correspond to the 3 phases of the electrical, the triphasic electrical grid, which is the, and basically this rotates here, and the electromagnetic field creates energy. So you make this move, you apply a torque here, this rotates, and then electricity is created in here. So let's apply Newton's law. Okay. So from Newton's law, this is the inertia moment of the turbine plus the rotator. So this is the total inertia moment of all that rotates, this and the turbine that also rotates, multiplied by the change in frequency must be equal to the mechanical torque minus the electromagnetic torque. Okay? You multiply by omega and define Pm as the mechanical power and Pe as the electromagnetic power, and you get this equation. Omega m is the angular velocity of the rotator shaft. Okay, the angular velocity of this. Yeah, mechanically rotating thing. Now, if you have a two-pole rotator, the electrical frequency is the same than the mechanical frequency. Sometimes you make rotators which rotate at a slower frequency, so you put more than 2 poles in here, okay? And then the electrical frequency is times the number of poles divided by 2 multiplied by the mechanical. You want this to be close to 50 Hertz. So depending on those poles, you design your system for a mechanical power, which is whatever it has to be. Okay? Now you put this in there, and you get this equation here. Okay? You introduce this coefficient, which is what engineers call the inertia per unit power. Basically, is the ratio between the kinetic energy at the rated angular frequency, 50 Hertz, to the ratio between the kinetic energy to the generator power, which I'm going to call PG. This is a generator that has a rated power of 100 megawatts. Okay? So they introduce this unit, this H. And then you get this equation. This is the swing equation. Okay? This is the basis. Okay? This is the basis. Now, this equation has only a fixed point if Pm is equal to Pe. Okay? Which means that the frequency can only be stable if Pm is equal to Pe. If not, omega dot is not 0, it's changing, whatever. So whatever values the omega takes is a symbol of the deviations between Pm and P. That's why omega, the frequency, is a very good proxy for these balances. Okay? And this explains what I have said before, and also about the inertia. Here is the inertia. The larger the inertia, the slower the change. But inertia does not provide stability. If Pm is not Pe, the system is not stable, no matter how much inertia it has. It will evolve slowly, but it will evolve out of equilibrium. And it will go away. Synchrony will be lost. Not yet, because I have not coupled this to another thing, okay? But synchrony. Okay, so that's the swing equation, well known in power systems engineering. Now, let me introduce a physicist model for a power grid. Okay? First, I have the swing equation, and an equation for the phase, which is just the integral of the electrical frequency. Now, I have to do something, okay? Because remember, PE is changing all the time. So I have to change PM all the time to make it closer to PE. And if not, the system fails. That's called primary control. Very similar to what James Watt did to the vapor machine, okay? He invented a regulator, something that was capable of stabilizing the velocity or the rotation angular velocity of the generator, independently that the mechanical torque that you extract from there was larger torque as well. Okay, it regulates the amount of vapor so that if you require more power, then it gives more vapor. So this is the primary control. Now the primary control only operates if the frequency is not the reference frequency. By the way, I have changed the notation in this transparency, so for that. Now omega is going to be here the deviation from the reference frequency, okay, and omega art is going to be the reference frequency. So this is the frequency deviation with respect to the reference. So it only puts PM if the frequency is not at reference, if not dB0. So this is what happens. You have a grid, you have a sudden increase in demand, primary control acts in about 1 second, and it stops the fall. You increase the demand, the frequency goes down, okay? Now it stops. But it stops not at 50 Hertz. Of course, because it just stopped. But so now you have to recover the 50 Hertz. That's what power plants has also a secondary control. What you do is you increase the power of the system with a proportionality constant to the frequency deviation, and this restores the frequency to 50 Hertz in a time that depends on the technology of the power plant. That could be in a few minutes or just 1 minute or whatever, okay? So if you close it here, you see the primary control that oscillates and then stops, and then, but stops, and then secondary control recovers the 50 Hertz. There are tertiary control, there is voltage controls, there are many, many other controls in power plants, okay? This is the minimum that you need to cope with variations in demand, okay? This is the physicist model, the spherical cow, okay? If you want to cope with variations in demand. If you don't want to cope with variations in demand, you can consider demand constant, and then you don't need this control, okay? And then you get even a simpler model. Now, what is the electrical load? The electrical load is whatever is consumed at the same node plus whatever is transmitted to another point, okay, which basically is proportional to the phase differences. I'm not going to enter in details of that, but basically this is equivalent to put the voltage difference, okay? I'm not going to introduce the voltage here, okay? I'm going to disregard that. And it could be also some renewable generator on the node. So we have electrical power. By the way, the load on the node, there is a part which is frequency independent. Okay, for instance, when you start at resistance, you switch on a resistance. Okay, that consumes the same energy independently of the frequency. But if you start a motor, the motor rotates synchronously. Do you wonder why many of the motors that are sold rotate at 3,000 revolutions per minute? Because the electrical frequency 50 Hertz. Guess what? 50 multiplied by 60. This sum is, yeah, well, you can say that the non-connector has a k equal to 0. That's the transmittance between node I and j. Okay, so so if there is no connection, it's 0, and if there is a connection, so you can, but if not, will be all the this is the adjacency matrix that you use. Sorry, a node is what is a node here is a physicist conception of that. It's basically a place where there is some conventional generation and might be some local consumption. Connected by a line. Okay? So a node could be the University of the Balearic Islands. That's a connectivity plan. Okay, so a node is a place and this is a power line. not necessarily, could be nodes that there has no generation. I'm going to go to that also. Okay, nodes are where there is generation or consumption, which is connected by a line. And you can make it as detailed or as coarse-grained as you want. A node could be a whole country connected to another country. That would be very weird. That will not be the electrical grid. Usually it's a substation. If we are talking about high voltage power grid, it's a substation connected by a high voltage line to another substation. Okay? But you can go down to mid voltage or to lower voltage, okay? To distribution voltage. It's the same idea. Okay? So for each node, you might have consumption, and also you might have generation, and you might also include some power that came from renewables on that node that do not follow the swing equation, because the renewables do not have anything rotating there. You have power electronics that provides some energy. So that's put together, and this is the model. So nodes with synchronization, you have all that, where I have added here something to force the power plants to operate at a given regime when they are more than one, because we know that maybe there are power plants that are operating at half the power and others are operating at 75%. So we force that with this PRF, each power plant, and the rest is the same, okay? The primary, secondary control, the transmission. And for the node without synchronous generation, what we do is we just take PM equal to 0. And we get this. And there is always some inertia, but because there is always some motor somewhere rotating, okay? There is no node in which you have never connected a motor, so that would be very bizarre, okay? Even a simple one, the inertia could be tiny, okay, compared to a huge power plant, but there will be always something. Okay, because there is always some rotating, always something. So that's the model. So that's for the nodes without synchronous generation, we have this. For the nodes with synchronous generation, we have this equation. Okay, and we put that on the grid. Okay, this is the model that we published it in 2023. Okay, there is some time-dependent inputs, which is the load at each node, the renewable generation, and the reference power at which the power plant has to operate. And then with that, we can use that to apply, for instance, to an island, because islands are nice because for many things, but which are detailed here, small systems, fluctuations important in small systems, large opportunity for renewables in general, whatever. And also because we live in an island, so why not? Okay, so, but we use a simple case, which is an island which is fully isolated, which is Gran Canaria, okay? This is the power grid of Gran Canaria. This is the power plants, the conventional power plants. They are located basically here and there. There are 3 power plants in each place, okay? This is steam turbine, you know, it's gas turbine, it's gas that is fired. This is the engine, and this CCGT is something that I'm going to explain in a moment. And there is also renewable, okay? The wind is the main energy, renewable energy source in Gran Canaria, okay? Because it blows all year long, day and night, okay? It's the trade winds, vientos alisios, okay? That blow all the time, okay? And there is now some installed power, 159 megawatts in 2019, which provide 40% of the total generation across the year, okay? Wind turbines are located over there and there, and we consider connected to these substations here, okay? And there is a little photovoltaic. This is already also probably there is much more photovoltaic now, but there is one. So what is combined cycle gas turbine? Combined cycle gas turbine is a conventional power plant in the sense that you burn something, okay? But you don't burn to heat and water and create vapor, as you do in a coal power plant. You burn this inside the turbine, like they do in a jet reactor, okay? So you inject this and you burn it inside this. So it operates at very high temperatures, okay? And then the combustion gases is used to heat steam and operate another turbine. So altogether it is very efficient, close to 50%, okay, which is a lot. Consider Carnot They're not efficiency, okay? They also has a very fast response because it's like if they are started, okay? When you go in a plane, engines start and they warm up, okay? And then when they are warm up, then they can move on. But you cannot warm up the engine right away because you cannot heat a material from cold to 100 to these temperatures. Just that, okay? I mean, it would take some minutes, okay, some time. So, but they don't have that much inertia, okay, because the size of these rotators is not that big because they are turbines, they are very fast design, okay. So now we can get data from demand from this web page. We use a load which is composed of the data of the demand plus noise to simulate the fast fluctuations that we don't have the data. We have data every 10 minutes. We use data from Red Electrica every 10 minutes on the generation for a given day. And we put all that in some parameters for the power plant. Some of them are known, some of them are estimated from the formula of power plants. We put all that and this is the data for the frequency, measure it in Gran Canaria at intervals of 1 second, and this is the output of the model for a given day. Okay, it's not perfect. If you look closer here, the fluctuation of the fast scale do not match because we only intend to recover the statistical variability, but it's not that bad. Okay, it's a very simple model compared to what is the whole power grid. Okay, so we can check the probability density function for the data and the simulation. It's not that bad. There is some here the data is a little bit bigger because there is fast variations over the shorter than a time scale of 10 minutes, which you don't have the data and we cannot reproduce by the synthetic noise. Okay, and basically it's quite very good argument. So that's the power spectrum of the frequency. So you take the frequency time series and do the Fourier transform, and not that quite close to the reality. Okay. So now we have a model that reproduces what Gran Canaria does. So now let's see what happens if we increase the renewable. That's why we need a model for, because now we can ask what if. Okay. What if? What if we increase the wind by a factor 2 or 10 or whatever on that day? Okay, what would have happened on January 19, 2019? Gran Canaria had installed the double of wind turbines that it had at previously. Okay, that was. Well, that would have been the frequency fluctuation because we increase the wind generation. We assume that all the wind generation, which is cheaper, is used, and we reduce the conventional generation. And this is what it shows. This is the 0.2 hertz, okay, not 0.15, because since in the islands there is more margin here, yeah, we consider already 0.2. Okay, now if we increase the wind by a factor 4, there is times of the day in which the wind gives all the power. And then the extra power is discarded. It is curtailment, okay? It's grounded to earth. On those times there is no fluctuations because you just discard more or less energy. But what happens is that the fluctuations start to grow. And if you increase the power by a factor 5, then there is more times of the day in which the wind provides the whole energy, but there is times of the day where the simulation is 1 hertz. Okay, you will never get to that. Okay, your system will have been failed way before, way before. Now, of course, this is curtailment, and so we can also test how much of this wind power is actually used. Okay, we increase this production, and so it turns that after increasing the wind by a factor 4, most of the power which is introduced has to be discarded. So this it depends on winter and summer, but basically after this we are not capable of generating more useful energy. So it does not make any sense. Now we can check at the frequency fluctuations when we increase the wind. This is the statistics, okay, by increasing the wind. As you can see, this is very dangerous, the width of the frequency fluctuations. And we can check what are the probability for fluctuations larger than a given threshold, say 0.2. Now, we can do another thing. We can see what we have to do to operate in this regime. So let's increase the control capability. Let's have conventional power plants that are just standing by for whatever is needed, even if they are not producing, just rotating without producing practically nothing. Okay, and we increase the power, the wind power by a factor 4, and then we increase the control capability by a factor 2, by a factor 4, and we check that by increasing the control capability, you can reduce these fluctuations. We can check how much is needed, okay, in this simple model. And you see that by increasing, for instance, the wind by 4 and the control by 4, basically you recover this, which is very similar to the origin. Okay. Here we did a study of how much control is needed, and we can also, because we have the model of the grid, we can say which are the lines that might become overloaded, okay? Because we are changing the production from this node, for instance, to this node, because most of we are going to use the wind here and not the conventional power plants there, okay? And we can check what lines might have a problem. Yes? In practice, what we do is we increase, in this case, we check for secondary control, we increase the capacity of response, the velocity at which the secondary control responds, the kappa. Okay, a little more technical, but that's what we have increased here. Yeah, or one with much faster response, or something that is operating very well and has a much capacity to grow. Okay, very fast. Okay. So that was the model. Now let me show another data analysis that we did. This is data analysis. What happened in the Balearic Islands, and this is all relevant for the discussion that we are going to have. I'm sorry, I'm getting a little delayed. Is basically what happens before and after the closure of Smurterà coal plant. Smurterà, which is this plant here in Alcúdia, has a lot of inertia, okay? And it was closed little by little. Basically, since 2021, there is only only 2 units out of the 4, and can only operate 500 hours a year. They are practically not operating now, but they are still there in case. But basically, I mean, this is the news that appeared in newspapers with different language in the island. And basically what happens is that the conventional, whatever the coal used to produce was now taken by the combined cycle, okay, the CCGT, okay? So when there was coal, this red, CCGT was operating low. When there was no coal, the CCGT is operating very large power, okay? So we take measurements on a location we consider representative of the Mallorca. The device, you can see it, is in Damia's office, okay? The box is still there, okay? And this measurement provides the data to the same database that we use for Gran Canaria, okay? That's the only one that we have in Spain, so we don't have data of this for the blackout of the 28th of April. I will take the data from Red Eléctrica. Let me show what happens on a typical day without coal, like today, or like nowadays, or whatever. You have the combined cycle. This is the cable. You see that the cable operates in a stepwise way, okay? And this is the demand and the different energy sources. There is some frequency fluctuations, and basically there's peaks of the frequency every time that the cable reaches the level of operation, because that's a ramp, and then the system has to adjust, okay, and it produces these peaks on the frequency every time they do that on the cable. The frequency fluctuations are sort of this is the cumulative distribution, the rank. So this is basically sort of a Gaussian, and it has a value which is less than statutory limits. Now let's see what happens in a typical day when we had coal. Okay, this is a typical day. This is coal. Well, the frequency fluctuation was bigger. And there is one particular thing. When they reach 0.15, the cable stops operating at constant power and starts performing control. The electronic of the cable starts adjusting the power of the cable beyond 0.15 to avoid it goes beyond, adjust the power, the demand, okay, whatever it is needed to avoid that. So basically you have this, before was something like this, now you have something like this, and then there is this cutoff, which is because of the cable action. So let's compare larger inertia, meaning when coal was there, with lower inertia but fast response. Okay? So which is without coal, which is CCG. Okay? As you can see, the fluctuations, and this is the density of the probability of fluctuations over the 3-month period, okay, has been reduced a lot by incorporating fast response, despite the fact that we might have reduced the inertia. Now, let's go back to April 28, okay? Remember April 28, so let's explain, yes. Combined cycle gas turbine, the one that I explained for Gran Canaria, okay? That's why I explained it. Which responds very fast. If it is on. If it is on. That's important. So what happened? What has been reported on April 28? Well, many things, okay? I'm not going to go. But here, Chataka, which is a sort of block, a technical block, had an atomic collapse, okay? And says, well, it turns out that there was a first thing and then a second thing, and recently have discovered something that they call the first thing that was before the first one, okay? So anyway, so there was a lack of power at some point, and a little bit there was another event, but now they have discovered that 19 seconds before the first one, there was another thing it up. Anyway, so we have a first thing and one previous, the second, and then after the second, the frequency below the critical value. In front of that, the converters on the photovoltaic plants that check if the frequency is within range and if the signal for voltage is within range. If it is not within, they disconnect. Bye-bye. Okay. Power plants, nuclear power plants, for instance, do the same. Okay. So in a little moment, we have lost 15 gigawatts. France and Morocco disconnect the cable. And the rest is history. So this is the set of cascading failures. Whatever triggered the cascading failures, we don't know. I don't know. Okay? I don't know. It will be known, but will require analyzing a lot of data. It hopefully will be known. Okay? But there is this cascading failure. Now, here say, cero energético, zero. Zero. It is said zero several times. Para restaurar el servicio desde negro, starting from black, okay? From zero, zero. Set, okay? Just keep that in mind. Now, on the same post, renewables in the center of the hurricane. Okay? Why? Blah, 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 renewables, reduce of energy, or reduce of inertia, makes the system vulnerable, blah, blah. Okay, you can read it. So let's analyze the energy mix. Okay, when you hear the energy mix, what they refer is what are the energies that were used to generate energy at that time. Okay, what was the energy mixed on April 28th at 12:30 before what is reported? Okay, this is the demand, the yellow line, we're generating over about 3 gigawatts more than we demanded. Okay. We were exporting to France, to Morocco, and to Portugal, and we were pumping water uphill for about 1 gigawatt of power, pumping water uphill. This is the renewables of photovoltaic. This is photovoltaic. This is wind generation. And this is hydroelectric. And I'm going to go into more detail. Okay, so we had, this is the proportion there. Okay, I'm going to do a more specific analysis. Now, the first thing is, wait a second. You have said 0, 0, 0? Is like the San Miguel 0, 0? Or not? I mean, it's 0, 0? Because this is 9 gigawatts. 9 times a nuclear power plant. Oh, 0. And is not. So what happens? Is the 0 much shorter? And 5 minutes later, here was already recovered? Doesn't seem to be so according to the news. So if the 0 was longer, what did they do with all this power? Was granted, was grounded, was curtailed to avoid, sent to ground to avoid problems? I don't know. I have not seen anybody reporting on that. Maybe somebody has done. I just have not found that. Okay, so that's my first question. What did they do with this energy? Where it went? 9 gigawatts of power is a lot of energy. Okay, little details. As Manuel says, the devil is in the details. Anyway, so let's go back to this part. Okay, 12:30. Okay, now at 12:30, renewables. So in Red Electric you can click and select, and automatically selects the renewable energy source. Okay. This is the generation by renewables. Okay, hydraulic, wind, photovoltaic. This is thermal solar, and this this thing. It is thermal renewable, which I think is biomass. Biomass. Okay, this biomass. Thermal solar. Okay, is a big farm of mirrors that tank to produce vapor. Now, renewables provide 26.2 gigawatts, more than the total demand of Spain, which was 25. Okay, 25. Renewables provided 1 gigawatt more than the total demand. The total generation was larger because we were pumping water, that we were sending electricity to France, to Morocco, and to all that. Okay, but renewables at that time were providing more than the total demand in Spain. Yes? No. If you do this and look for other days of April, there is times of the day where renewables provide 81% or 80% of the generation. That was not exceptional as well for this time of the year. Now, I didn't put all other days because I thought that was already too long. Okay, but now here they say conventional is not true. Okay, I want to say the non-renewable power plants. Okay, because hydraulic is renewable and conventional. Okay, so the upper title is wrong. The non-renewable power plants, okay, provided this energy. Okay, at the time of this, they provided 6 gigawatts, which is 18.5% of the total generation. Okay, by the way, after that, nuclear is disconnected and remained disconnected until the next day at 9 p.m. Okay, coal practically did nothing, and who take the job to bring this back? Okay? Combined cycle. Nobody talks about combined cycle, okay? Yeah. That's the data. Of course, maybe everything this is wrong, because if there was an absolute zero, maybe all this data is wrong. I don't know. Because this does not match the total zero that was here, okay? To be with that, I don't know. Now, the interchanges. The interchanges stop at the blackout. There was no interchange, according to this data, again, can be zero, until a couple of hours later. So it is true that France interchange held 2 hours later, not immediately. That's the official data. I cannot say anything because I don't know anything else. Okay? And this was France, okay? Of course, Portugal cannot help because it was in the same situation than us. But, by the way, on Balearic Islands, we had a link. Why we didn't send power there? No, we didn't send any power. I don't know. Anyway, so how much inertia did we have? Did we have enough inertia? They say that when there is low inertia, the system is very vulnerable and can fall. And yes, maybe. But so what is that? So in this forum that I put there, okay, that is a forensic analysis of there's a lot of details. They say that the synchronous generation, when it is safe, is because they say, okay, and they say because they have talked to us. The synchronous generation, well, the system is unstable if the synchronous generation falls below 30%. At 12:30, the synchronous conventional plants, the thermal plants and nuclear plants, okay, thermonuclear, because nuclear is a thermal plant, okay, provided 6 gigawatt of power. This is only 18.5. But is that all the inertia? Wait a second. Hydro is a synchronous generation, which is renewable, but is synchronous. That was 3 gigawatts. Thermal renewable is also synchronous, is a turbine gas, vapor, which is heated by biomass. The thermal solar is synchronous because you heat a tank to make vapor and rotate. So maybe we were missing this into counting the inertia, or why they are not counted. Usually, sometimes the hydro is included, but I have not found any place where they include the thermal solar as a source with inertia. Why? I don't understand. I mean, I'm not an expert in power plants, okay? Just don't understand. Because if I think it operates, I don't understand why the inertia is not accounted. And then there is another thing, which is also curious. Wait a second. There was 1 gigawatt of pumping. That's a consumption. Yes, but it's a consumption of big mass rotating at 50 hertz or synchronous, okay? And that's like a hydroelectric turbine used the other way. But for inertia, you only count the mass that rotates. It doesn't matter if you produce electricity or use electricity to pump water. That's inertia anyway, and it has to be added in positive because it's total inertia, okay? That's physics. I don't know. I mean, I'm missing something, but maybe it's not the same power plant. Maybe it's an electrical engine, okay? Different, but still, that has some inertia rotating. Any motor has inertia. Okay, I see. So let's do the counting again, okay? So this is the conventional power plants. This is the 6 gigawatt, but all this in blue is the inertia. And when you count that, you got 14 gigawatts of inertia, which is 44% the total generation. That's quite over 30%. Was the inertia too low? Was inertia, the lack of inertia, the problem? Or was the fact that we had less than 1 gigawatt of combined cycle operating at that time? So we have very few parts. We have 22 gigawatts of combined cycle installed in Spain. We are using less than 1 gigawatt. Maybe we were using 2 plants or 3 plants or whatever when we have many of them. Were all the others disconnected? Of course, you cannot put increased power immediately, something that is not operating, because I told you before, you have to start that. Maybe we were operating with very few control capabilities. Maybe we need no inertia, which maybe we had enough. Maybe we have to have control. We have to operate the grid in a smarter way. To finish. And the Balearic grid. Well, that's the Balearic grid. That's the cable. It stopped at 2:30. It was carrying 100 megawatts. 50% the total demand at that time. 50% of the total generation that we had disappeared when Spain, in a few seconds, when it happens all that. What happens in the Balearic Islands? Combined cycle went from 279 to 382. It took the 100 megawatts, and that's it. I may be wrong, might be just a casualty, but it is clear that having a fast response, this is not the cause of the trouble. This is when there is a trouble, how you cope with that. Okay? So, combined cycle helps, and this is that one thing, and it in principle should help more than the frequency. Now, this plot is very bad. There is no data on frequency fluctuations, official data on frequency fluctuations in Spain. Okay, this Red Eléctrica does not publish that, but there is a person that has published that. You go to the block and you see this in more detail. This is the blackout. Okay, and this is about 1 hertz. So if you go to hertz, I excuse you to say what happens. Okay, the blue line is Spain, and the other lines are different places in Europe. Now, the curious thing, 15 minutes before the blackout, there was also a set of larger fluctuations in Spain, and 30 minutes also larger than the rest of Europe. That's the excitation of modes, can be the excitation of modes. When you go in a boat, the pressure that moves less in the middle. Okay, if you go to one of the extremes of the boat moves more. We are in one of the extremes of the European grid. Okay. So yes. Not in here. But there's some data. There is some. That's true. There is data in which you see oscillations which are anti-phase with the ones in Spain. So, but this is a consequence, maybe, or whatever. But there was here already some fluctuations that were exciting this. Okay? This is in this block, and I'm not going to give you conclusions. I'm just going to tell you this, which I think is sort of a conclusion, is that you might not be aware, but a couple of days ago, okay, just on May 8th, there was a blackout in La Palma. Okay, one substation got disconnected, the chinchos. Okay, and it says the fall in substation or chinchos introduced a disbalance between demand and generation, which derivated in the connection of several equipment to protect the equipment, and it triggered a big blackout. again, whatever happened in Spain in another way. Okay, something happens, and then a cascade of events. And with that, I finish.
Well, thank you very much.
I apologize
It
for
was a
the.
bit long, but it was an extraordinary event, so an extraordinary talk. Okay,
No.
so any question?
You just told at one moment that during the blackout there was all these control mechanisms that started all at once, no? That they stopped.
No, it's not that they start all at once, because it's that they look all at the same information, which is the frequency.
But at the end, they all started at the same at one because the frequency.
Sometimes it's at once, and sometimes it's a cascading. So imagine that you disconnect one line because it's overloaded because of something changed. Other lines might become overloaded. So when this one's overload gets disconnected, it might overload a third one. And it could be, it's not that one at the next nanosecond there is 10 out. It's that usually it's a very fast cascading of things. Okay?
But I was thinking, if, for example, if you stop a solar plant,
Yes, but why a solar plant stop?
because well, you said that it dropped the frequency, then it stopped.
So
The frequency should go
it stopped
up.
because the frequency dropped. So what was the cause of the frequency to drop? I mean, say, yo, that solar power plant stopped. I mean, if it was sunny, there was no meteorological inconvenience there. Why it stopped? The electronics of the power plants for big, I mean, there is solar power plants in Spain which just up to 500 megawatts. They are big, okay? In Badajoz, for instance. But they don't have one single electronic system, okay? They have several. And of course, it might fail a part of the plant, but not the whole plant. What is the single thing that makes full stop all that? Maybe that the frequency is out of range. But then if the frequency is out of range, what triggered that frequency to be out of range? Okay. So usually in many of these blackouts, usually it's an incident that drops one line or one power, or like the tree falling into the line and breaking the line, or maybe some generation was discontinued, disrupted because somebody pressed the wrong button or whatever. That happens in California. There was one big blackout that somebody started a pump to pump water to California because that was in a dry season, starting a lot of pumps in a moment in which the grid was the limit, and yeah, blackout. California, Baja California, Sonora.
Thank you.
And then, okay, so let's assume there's this initial drop in frequency. So then why do the solar plants disconnect from the grid?
The inverters, well, this is something to be explained a little bit more. I have no time. There are two kinds of, well, there are many kinds of inverters. So you have to convert AC to this, DC to AC, okay? So the most old inverters, the first one was called grid following inverters. Okay, so you need a signal to generate the frequency, and you just replicate the signal that you get. If you don't get signal, you don't generate. If the signal is distorted, there is a mechanism to say, well, if it's distorted, stop. Okay? So if the frequency is out of range, if the voltage is out of range, stop. Okay? That's the grid following. Now, there is another kind of electronics which is more modern, and there are some power. This is another thing. There is some of this solar photovoltaic generation which has grid forming inverters. And grid forming inverters has an electronics that they do whatever they want with electrical wave. Okay, it's like a battery. Okay, a battery that the side it generates the pure electromagnetic wave out of a chemical thing. Okay, which a battery give a continuous a DC volt, a DC current, and then in the side there is electronics that give you the perfect sinusoidal wave. So if you have grid forming inverters, which what the size has, then you can emulate inertia. You can emulate control using the battery as a backup. Must have some battery there, okay? Might be more special. So part of the photovoltaic also has inertia. Not very much in Spain, okay? But part of it, which I have not accounted for, okay? Because I don't know how much. So yeah, I mean, there are different situations. You have to see really the power plant that fall, what kind of systems they had, what was there. I don't know what happens. So it's difficult to say it without more detailed knowledge.
I think it's time to stop. All right. So you
Okay.
have. Thank you very much for coming.
Mucho la charla. He visto mucho estos días gente quejándose de que esto también era un problema de que la red es como muy grande, ¿no?
Bueno,
¿Por qué
porque
no tener
ustedes dicen que cuanto más grande, mejor.
más grande mejor? Pero por lo que has contado tú, ¿no sería mejor tener
Pero
algo mayor que
te dicen
cada
que
cable?
cuando tienes una red muy grande, entonces una pequeña perturbación son